Thank you for the introduction. Oh, I have to start my presentation. In the next couple of minutes, I want to talk about a subfield of microfluidics, which we call Thermo-Optofluidics, which basically is the combination of microfluidics and optics on the same chip, which is also referred to as optofluidics, and the inclusion of temperature as an intended parameter. This work is part of the European project NCABRA, and as already mentioned, was done in a collaboration between the University of Bremen in Germany and the Vienna University of Technology in Austria. At the beginning of my presentation, I first want to give a short motivation of why this Thermo-Optofluidics could be of interest and for which application this could be of interest. Here I will talk about the thermo-optic coefficients of liquids and solids and want to point out the major difference in the coefficients of those two materials, which is actually the major point or the main point of this research. Also want to show you the device design which we use for the on-chip light modulation, and finally give you some first experimental results and conclude my talk. Many physical properties, maybe even all physical properties, are temperature dependent. So if we, for example, think about a thermistor, this thermistor has a different value of resistance at different temperature. Often seen as a disadvantage, this temperature dependency of properties can also be used intentionally for sensor applications. So if we just think of a temperature measurement unit, for example, as well as for actuator principles. So here I mentioned the thermo-optic switch, which I will talk about more in detail on the next slide. For both the such sensor elements and also for actuators, a high temperature dependency is desirable. So, for example, if you think about the temperature sensor, if for a given temperature change the impact on this physical property is higher, we can resolve smaller temperature changes. And also for actuators, an increased temperature dependency results in improved performance of the actuators. And this is actually where we focus our research on, to increase this or to obtain a higher temperature dependency. Let's have a look at a thermo-optic light switch. As published by Espinola et al., they integrated an on-chip Mach-10 interferometer, which basically consists of two arms, where the light is split and joined at the end again, and one arm of those two is or can be heated by an integrated heating element. With that, the refractive index of the material, in this case silicon, is changed, which creates a phase shift and can be used for light modulation. In this publication, a temperature change of 8 Kelvin is necessary to obtain a phase shift of pi in this upper arm, which means a full on-off modulation of the light. Given this arrangement, this group could reach a cutoff frequency of light modulation of 50 kilohertz at the wavelength of 1.5 micrometers. The temperature dependency of the refractive index of silicon is 1.84 times 10 to the minus 4th per Kelvin. If we now imagine that we can increase this coefficient somehow, this would mean that a smaller temperature change would be sufficient to reach the phase shift of pi. This means that the cooling and heating times would be shortened, and we could end up with an increased overall cutoff frequency. And this is where liquids come in. If we have a look at the thermo-optic coefficient of liquids, we see, so here there is a table of several liquids, but let's, for example, stick to ethanol. We see that the magnitude of this coefficient is much higher compared to, for example, silicon, given in the previous example. And the second most interesting thing is that this thermo-optic coefficient is negative. And for solid, or for most solids, and also for silicon, this is positive. If we now think of a sophisticated combination of liquids and solids on the same chip, we can end up with an increased effective thermo-optic coefficient by a factor of even more than 2. To show that this principle is working, we build up a liquid core solid cladding waveguide on a chip. That means that we use a microfluidic channel, here illustrated by those red lines, which we filled with our core medium, a liquid. And the surrounding chip material, so all this white part here actually, is the cladding of this waveguide. Light is coupled onto the chip into the liquid core solid cladding waveguide on this side, and at room temperature, most of the light is guided within the core of this waveguide and reaches the output, while if we apply a temperature change, the index of refractions of solid, of core and cladding change, which reversibly switches off the light guidance, which is shown in this lower schematic. If we have a look at the refractive index profile of this waveguide arrangement, here in the first case at room temperature, we see that the refractive index of the core solution exceeds the index of the cladding material, which is the essential criteria for waveguiding by total internal refraction. At altered temperature, we see that the index of the core medium of the liquid actually got smaller, while the index of the cladding increased. And at one point, light guidance cannot be obtained anymore in the waveguide, and the light guidance is switched off. The experimental setup we use for our measurements looks like that. We have the chip bonded on a glass microscope slide. In the first studies, this chip was out of PDMS. This glass slide is placed on a Peltier element, which is responsible for the temperature management, and an underlying heat sink. For the peripheral light guidance, we inserted 2 glass fibers in the chip. The first, the input glass fiber, where we have the external light source attached at the other end. In our case, this was a green laser. And the output glass fiber, which is attached to a photodetector to record the signal, which is coming out from the liquid core solid cladding waveguide. One important criteria for the functionality of this light modulator is index matching. The index of the core solution has to slightly exceed the index of the cladding. In this case, we get a normally on configuration. That means that at room temperature, light is guided through the waveguide. To choose the right index of the core solution, we recorded the output at the photodetector depending on the calcium chloride concentration. We use the calcium chloride solution as the core liquid. And at a certain point, the index of the core solution increases the index of PDMS, and light starts to be guided through the waveguide, and the optical output increases. To obtain highest sensitivity, one has to choose calcium chloride concentration, so a refractive index, right after this critical value. So we chose a value of 3.1 mole per liter calcium chloride. The results we obtained look like that. Here we see fluorescent images. For this reason, our PMS devices were soaked with the fluorophore, in this case rhodamine. And in the upper figure, we see the situation at room temperature. Here we see that most of the light, or the biggest part of the light, is confined within the waveguide and excites a more or less huge fluorescent signal at the output, which can be seen here. If we now change the temperature, light guidance is switched off, and there is no fluorescent signal visible anymore at the output. If we have a look at the recorded signal, we can see that at room temperature, the optical output recorded at the photodetector is high. If we go to the altered temperature, the optical output decreases to the low value, while immediately increasing again to the high value if we go back to room temperature. This on-off modulation can repeat it more or less as many times as desired. The relatively long time constant in this experiment is explained by the quite bulky experimental setup. You have to imagine that both the whole PDMS chip and the glass substrate has to be brought to the same temperature so that this light modulation sequence more or less is finished. If we think of an integrated version of this heating element, of course we will end up with much faster switching cycles. The conclusion, we have shown that the combination of liquids and solids enables promising new opportunities for thermal application. So here especially the fact that the thermo-optic coefficient of solid and liquid have opposing signs can be beneficial for the implementation, for example, of an on-off light modulator, which with actually increased switching capabilities, so switch frequency by a factor of more than 2 compared to solely solid realizations. With this, I'm already at the end. Many thanks for your attention.